I want to thank everybody for joining us today. I'm Jason Hartshoe, the OSU Extension Field Specialist in Dairy Management and Precision Livestock. This is our first in our inaugural Precision Livestock Farming series that we're hoping to do each winter of Zoom meetings looking at different species and really including forages into that precision livestock side. So today's presentation, I'll be focusing on using precision livestock technologies to assess forage yield and quality. For that, we have with us today Dr. Josh Jackson with the University of Kentucky Biosystems and Agricultural Engineering to tell us about some of the things he's been working on.
All right, yeah, I'll just jump right into it. So, as you said, I'm Josh Jackson, University of Kentucky. I'm originally born and raised in Kentucky, and I grew up on a beef operation just outside of Lexington here. So we have about 60 registered Angus mama cows, and we're looking at some of the interest we had was initially looking at how can we use some of these new technologies, specifically drones, to solve some of our issues. And so, with the beef operation, the cattle being dispersed across the farm, these drones can be an effective tool of finding a lot of these animals which are spatially distributed on these operations. So, using this as a tool, a lot of people we thought were getting this as a toy. Can we also integrate a usefulness or find a way for producers to actually utilize this if they already have some of these on their operation? And so one of the things I wanted to show off here on this first slide here, so our drones there on the right, and then we have a couple, like three small dots there. That's some black vultures. So we're actually flying at our UK beef units. And so when we're doing circular flight patterns, so are these black vultures that came around and circled us as we were circling some of our alfalfa plots, and they were circling around us, seeing what had we found something or not. So then we tried to use our drone to chase them off a little bit, and definitely did not work. So they're much more dynamic and agile in 3D space, and we just let them be at that point. But that was kind of a learning experience for us. So just a general outline of the presentation I'm going to have here. So I'm going to talk a little bit initially about just some yield and quality, go over why it's important and what we're thinking about with quality aspects, and then talk about what's one of our major challenges, it being the weather, and then moving on into some of our remote sensing options with our drones or UAVs being one of them, and going from there into some of our sensors like red, green, blue, our regular sensors, LiDAR, and and finally closing out with our cost aspects. So, nutrient requirements, I think we all know that, there's going to be differences between animals. And so I just had this slide to show that one animal here is going to take more groceries than the others. So is there, what the reason the forage is going to be important, is going to be based upon our age of our animals. A lot of times we're asking for our first calf heifers, we're asking them to grow, rebreed, and then still lactate. And so they're going to have a very, very high nutritional demand on them. So we need to make sure they get the best forage possible. Thinking about level production, we've again known this for years that as you increase that level of production, they're going to require a more and a higher quality forage as well. Knowing that there are differences, going to be differences between breeds. Thinking about our physiology, if ones are in lactation, are they going to require more than ones that are gestating animals? And then thinking about our environmental differences, in the season, especially for this time of year, our beef animals out in the pasture, they're having to deal with a lot of mud issues right now, at least here in central Kentucky and throughout the state and surrounding areas. So, those, that requires, again, 25% more energy based just because they have to fight through the mud. So being able to allocate additional resources to them, then, it's going to be other factors that are cause some individual variation amongst the animal as well. So just taking into fact, we know that there's the nutritional requirements of the animals, but then thinking about on the flip side, so we got our animals and we have our machinery. So the point of our machinery is to try to optimize our forage yield and quality for livestock consumption in a timely manner, a timely but cost-effective manner. So in this case, it's definitely with that Claas Cougar, be able to do it relatively quickly, but it's going to be cost-effective. And thinking about, when we harvest is going to be important. So I know we've all seen this graph probably in similar extension presentations over the years, but thinking about our forage yield versus our quality. As we're able to increase that yield, this is true for a lot of forages, our quality is going to decrease. And so if we're using some low lignin varieties, those can actually buy us a little more time. And so our typical schedule, we're trying to cut approximately every 28 days is our harvest schedule. But with some low lignin varieties, we can buy about 7 more days and still maintain the same quality, but increase the potential yields. The challenge is, for that 28-day harvest is that not all fields are going to be the same. And so how much can we extend it? When can we really extend those harvest intervals as much as possible? Because we potentially extend those, get a little higher quality. Maybe we don't have to harvest nearly as much throughout over that season, so we can reduce to some degree the cost associated with this harvesting equipment. And so if we have to, think about one of our major challenges to this 28-day harvest window, and I harvest hay myself, it's going to be the weather. And so thinking about the weather, we have to think about our speed of operation, like how many acres do we need to put down? How fast do we need to get back up? What's my number of drying days? Let's thinking about what's my potential for harvest losses. I'm trying to avoid that potentially getting rained on, and just thinking about overall ease of operation. If I'm buying newer technology, is that helping me operate more effectively within that field? And then the other big, we're thinking about our machinery is think about our ease of repair, ease of acquisition. I think the big challenge for a lot of people right now has just been getting parts potentially and supply. The word of the day seems to be supply chain issues still being a challenge for a lot of producers. So think about our available baling days. I want to hit this really quick. Weather being the big challenge. So here in Kentucky, so I have Lexington, Bowling Green, and Paducah shown here. But I just wanted to go over. We're seeing. We're looking at a 4-day window. A 4-day window for baling hay, and we kind of evaluate this across our season, so from May to September. With this 4-day window, what we're looking at is primarily it's based upon how many consecutive days of rainfall. We have to have 4 consecutive days where it's not rained, and then we consider that 4th day our baling day. So how many baling days are available? It looks like for Lexington across Paducah, we have about 40 baling days for our producers, and so that was just, it doesn't necessarily mean that it's going to be the right climate, the right temperature for drying. It doesn't necessarily mean that you're not going to have overcast skies. It just means that there's 4 days in which did not rain. And so that's the maximum that we could have is kind of this 40 days across them. But looking at, our past somewhat five years essentially. And so we see that those available baling days are somewhat decreasing, especially in May, to some degree June, a little bit in August as well, surprisingly. And we see kind of a mixed effect in September. But on the whole, we're seeing this decrease in our baling days. So we got to be more and more efficient. And if we can extend the interval, maybe that allows some flexibility with this. So if we look specifically at May, so I wanted to just take May into account. So we saw that was decreasing over the past, kind of 5 years. We can see that within May, our average, was about 6 baling days that we could have in May. It varied, between the cities. So some days it was, some years it was actually 0 in some locations, and others we're seeing about 20 days. But what happened in 2007 and 2012, those are both years in which we experienced fairly significant drought. So it started in May and then kind of just kept on going. So this could be a concern. So we had a number of baling days, but after that, subsequent, we didn't really have the rainfall to provide adequate forages. So if we have wet, it's kind of a catch-22. So we either have the baling days and we don't have the forage later on, or we do, and we just have to be really efficient with our time. Just to show some of the variation that can take place here, I brought this graph up. So we have our average temperature on the bottom x-axis, and on y-axis we have accumulated precipitation. And so I just want to show 2018 and 2019. So at the top right here is 2018. So that September we had, past 20-year span approximately, we had one of the wettest and warmest Septembers. And then the very subsequent year, we had the warmest and driest September. So between the years, we can see definitely see a lot of variation taking place. And so, how do we account for that? So one of the tools I think we have down here in Kentucky, and I'm sure there's equivalent resources up there in Ohio and across the U.S. at different universities, is we have our point ag weather forecast. So a lot of times for producers, we can click on our individual counties within here and get a more detailed estimation. So I do like this one that does includes rainfall total. So I pull this off Tuesday. But rainfall totals and the percent, chance of rain, our chance of rain. So it includes, for me, it's important because, if it's 0.07 inches of rain or 50% 6% chance, that's going to be different. It was a 1 inch of rain and a 56% chance. So how I respond to those can be different because I can still cut hay one day. Oh, that's all the 10th of an inch of rain. I'm not really too concerned. But if it's an inch of rain, yeah, I'm definitely getting concerned. So I do like that fact that we have that in ours. And the evapotranspiration rate. So the evapotranspiration, so right now it's showing 0.3 and to 0.7 across the board going out to Sunday. But I do like this aspect because, when we get into summertime and it has for far left, what's our drying conditions? We want to see that to be at least 0.2 or 0.21 for good drying taking place for our hay. The other, county specific information, it has at the bottom, one of the bottom rows here. So next to last row down here is our drying condition. So I like that fact that, this is a resource available to our producers. Whoops, let me go back a slide. And so, it helps you estimate or, look at, what's my drying condition. It's going to be good, fair, poor, and kind of has that stoplight philosophy. Green means good, yellow means you watch yourself, and red means don't go. The other aspect I do like about this, county specific data, we got some sky cover again, and we also have the dew and tells you whether you're going to have a moderate dew, heavy dew, and so that can help you estimate how quickly you can get out in that field. So, with weather being one of our big challenges, we're trying to get this as an application available to producers across the U.S. To help them estimate, how soon and how easily can get out into that field. From a current technology standpoint, we think about, some of the automation taking place. And so our ISO is fairly important. So ISO connection, ISO 2 or ISO 3, allowing for some of that automation control. So it eliminates the need for a separate monitor. So you have a common monitor for your multiple implements. And I think it provides more control, at least for some of your round balers. You can automatically stop, wrap, and eject the bales for some of those ISO 3 controls. And it gives you a little more data we can pull from our tractor. And so we can also pull into our baler monitors. So we have this, we can get a yield map, similar to what we can produce for corn. We can also produce this for our balers, or larger square balers can produce these as well. So you can get in real time, the weight of the bale, your location, your moisture, your number of bales you're producing within that field. Some of them have the capability to apply an RFID tag. You can indicate if there are weeds going to be present within this bale, twine, and then if you're applying any preservative to that bale. So it gives you a lot more resolution, a lot more ways, and then you have the option to tag certain bales. The capability to sort them easier if needed, and to look at how is your field producing, how is your yield potentially within that field. And so there's multiple companies. So John Deere, AGCO would have these yield monitors. And also John Deere has an option as well when you have your forage harvester going through the field. They do have ways in which they can estimate the yield or the flow rate of material through your forage harvester as well. So as long as you keep that calibrated, and usually they're calibrated for either 100% grass or 100% alfalfa, just keeping that into mind as or you can have our yield monitor. That'd be another way to potentially measure what's taking place within our field and how do we account for that variation, how much total nutrients are we pulling off those fields, and how we can better allocate those nutrients in the future. Something I did want to mention, so I did see this at the National Farm Machinery Show last year. It was a little different. So this setup here, they had the semi truck here, and it had these spikes, so these 84 spikes, and you can put up to 6 bales across here. But I just wanted to mention it because it could be, with weather being one of the challenges, and you'd have to do a lot of, put your pencil to paper and do your cowboy math and see if this would actually pencil out for you. Because it will require, sunshine. I always say sunshine's free for drying, But anytime we start applying diesel fuel, other costs, but becomes more expensive. But if it allows us to maybe bale that a little wetter, or if we do have to bale it, due to weather issues with weather, then we get these bales dried down. And so this was a system that they had at the National Farm Machinery Show. I haven't seen any journal articles about it yet, as far as its effectiveness. But what they had was this product was you put the 84 spikes to the bale, it would force air. It has a relatively large diesel engine to force air through those bales. And then it was taking it from, it could take it from 30% moisture down to 18% moisture within about 10 to 20 minutes, depending. And so this was an interesting option. If weather is our challenge, this could be one option available to producers. So I just want to mention some of the current technologies. They had this at the Farm Machinery Show this past year. I'm not sure if they're going to be there this next year. But some of our other, current technology has to do with remote sensing. So what other ways can we evaluate, the quality of our forages in the field? And so a lot of it, traditionally has been based on, it was ground-based. We're going out there, we can take a stick and measure how tall is our crop to get a good stand height. We can have satellite-based, that's going to be, I know Elon Musk can throw all those satellites out there, but, there's different satellites there to look at different nutrient qualities and take imaging, but it's not going to give you very high resolution when we're looking at our field level resolution. And there's options available for, if we're looking at alfalfa or crops, there's options available for manned aircraft, and there's also options available for UAVs, or so our drones. And so from a cost standpoint, our drones give us a lot of flexibility. So they're going to be probably our lowest cost option, and give us one of the highest spatial resolution. So, and they're very nimble in some of the small regular state fields we have in Kentucky, but they're still very useful in some of the larger fields. And they're somewhat susceptible to weather, but if it's storming, blowing down rain, I think the manned aircraft and satellite aren't going to be seeing much anyway. So I think they're not going to be they are potentially a good resource to have. So for these drones, and so they're referred to as drones, they're unmanned aerial vehicles, unmanned aerial systems, so UAVs, UAS, remotely piloted aircraft, remotely piloted vehicles. So a lot of different names, and they can vary in size from fit in the palm of your hand to I think the T-40 I think is about 200-pound drone, fully loaded. And so they can vary widely in size, and so most of the ones if we're using for imaging are going to be below 55 pounds. That's kind of one of our classes. Well, I'll get into that regulations here in a little bit. So types of UAVs, so there's fixed wing, we have multi-rotor and hybrid. Most of them are going to be multi-rotor because the multi-rotor gives a lot more flexibility as far as our takeoff and landing. So we can take off and land pretty much anywhere. It was the hills of Kentucky or down close toward Tennessee with a lot of flat open fields. You can get a lot of just dynamic applications with some of those drones. So what's shown here is like an older sprayer drone, multi-rotor drones, and then there's also hybrid drones, but there's also, if we're going further out west, fixed wing if we want to cover a very, very, very large span of area as well. So lots of different options, and I want to make sure to mention that there are regulations. So if we're using this for commercial purposes, we're going out there inspecting our crop, we're using it for commercial purposes, we need to make sure to get our Part 107 knowledge test. And so this is through the FAA. The knowledge test costs $175 initially. So you pay that $175, you take the test. It's a 60-question exam, and you get a 70% or greater on the exam, and you do pass it. And the knowledge test itself is good for 2 years, and each subsequent year you just have, or after that 2-year period is up, you just have to take an online test, and it's free. And so the UAS, our drones must be registered with the Federal Aviation Administration. It's only $5, and it's good for about it is good for 3 years. Some of the bigger drones are now good for 7 years. And another thing we have to think about is our airspace. And so where we're flying can be important. So this is one app, and there's many others. So B4, letter B, number 4, letter U, Fly app is a good one to at least getting a good estimation of where you are. Make sure we do a notice to all airmen as far as we're flying in this certain area. So for the knowledge test, the Part 107 knowledge test, as part of our commercial regulation, 90% of people pass this. And so I was looking the other day, we have almost 370,000 individuals, who are commercial drone pilots here with the US. And we still have to maintain visual line of sight, but there are waivers. We can have autonomous flights, but we need to still maintain visual line of sight. However, there are ways we can get waivers to operate beyond a visual line of sight as well. And so there's going to be certain regulations associated with our just knowledge of the regulations, knowledge of our airspace, weather, loading, and operations. And 60 questions. Again, they have to get 70% or greater on that exam to pass it. But most people, like I said, most people do pass this exam. And we think about our airspace. So anytime we have our prohibited restricted airspace, so it could be around our blue here shown, our Fort Knox and other military installations. It could be where we have a towered airport. So towered airports in Louisville and Bowling Green and Owensboro, they're going to have more restrictions around 5 nautical miles around those airports. We cannot, prohibit it from flying within our national parks. So there's certain areas in which we can't fly. Then we also have to think there are non-towered airports, and there's a whole lot of non-towered airports and heliports throughout, Kentucky and Ohio. There's a lot of them. And so, but a lot of these is just you maintain situational awareness. If there is aircraft within your vicinity, go ahead and land. And so this is a similar thing for Litchfield. We can see here that there are right there in the center of the map is Litchfield or Grayson County Airport. It technically has a Class D airspace, but it's 700 feet and above, so you can fly below that. So a lot of times, within the vast majority, as long as you're not next to a military installation or a towered airport, you should have the ability to fly for the most part. And I always encourage producers, to go ahead and get the smarter drones, to have ones that can hover, that have collision avoidance, that you can program into a flight path so that you're not worried about trying to fly, learning to become a good pilot. You're really utilizing just that as it should be, as a tool for collecting visual images. There are multiple power sources. They're coming out within the future here, probably some wireless charging options, but right now we're pretty much stuck with lithium polymers, but they are creating more and more efficient batteries to help us increase that flight time. So your average flight time is going to be anywhere from about 25 minutes, maybe up to 50 minutes, depending on the size of your drone. With data transfer, traditionally when we started this with the Phantom 4, you were limited to 64 gigabyte SD card. Now we have drones that themselves have about a terabyte of storage on the drones themselves. So that's gotten a lot more flexible with some of these newer drones. But jumping into it, so I kind of got that introduction there. So thinking about our forage crop, thinking about our alfalfa, what are we really looking for here? And so, here we have some pest damage taking place, but we're really trying to predict, what is our yield? What is our forage quality? And so trying to figure out how much is available in the field, we'll go through there with a hay bind or a disc bind and cut a swath out and look at it from a side view. We can get a pretty good estimation from that side profile of, what's available in that field, if it's a thick or thin sample. From a top view, it can be a little more difficult. That's why sometimes our camera angle and the number of images and overlaps that we get will be important. So, drones, we're thinking about, the unmanned aerial system. We collect our imagery, we process, get a surface model, the DSM, and digital terrain model. What's our ground, and then the difference between the two, getting our crop height models, and then taking that, getting a good yield estimation from that. And so for flight parameters, I want to just mention this. Most of them are going to be in a apostrophe. They'll be in a grid pattern. And so we'll have some front overlap taking place and some side overlap taking place as well. And so at the amount of overlap on the front and side will, as we increase that, it's going to increase our flight duration. So over the same area. In this case, we have our side overlap varies as the front overlap is constant. So the blue line, so we get above 80% on both of these values, and it seems to really increase the duration of our flights. So the image overlap is going to be important because the more overlap we can get on some of these images, the more tie points that we have, and the easiest for it to merge those different images together, especially when we have a uniform crop surface like in alfalfa, where we have it's fairly uniform crop surface. And so we can get a much better estimation of some of the parameters we're looking at. Similarly, especially with regard to crop height, which is our main concern. Similarly with altitude. Altitude, we're looking at as we increase altitude. So it's x-axis, so it's the altitude. As we increase our altitude above ground level, the number of acres we can see is going to increase. So if we go up to 400 feet above ground level, we can cover about 100 acres. But we've reduced our number of images collected, which can be both good and bad. If we reduce the number of images, we can process the files faster and get a quicker analysis. However, that will also reduce the spatial resolution, so maybe we can't quite make as detailed of analysis as possible. So that's the catch-22. Whereas with flat low altitude, we can collect a large number of images, a little harder to analyze, but we're not covering near as much area. So just finding the balance between those points is going to be important. And then from there, we have some post-processing that takes place. So how are we combining all those images? So we have a lot of individual images, and then we Pix4D, drone to map, QGIS, drone deploy. So Pix4D, drone deploy, and so they take all those images and merge them together with those different tie points, and then we take it into ArcGIS or QGIS and then analyze it further if needed. But here, I want to talk about, right here shows a general flight plan. So this is off of drone deploy, but it could be just the same with Pix4D and other programs. But from our flight plan that we put into our tablet or other device, we have here, where's our start point? We're in a typical grid pattern. And, at this point, we're flying about 95 acres in about 22 minutes. And it says it takes 2 batteries, but actually take about 1. This is a certain amount of overlap. We can, if we want to really increase, level of detail, we can actually go from a standard grid pattern to we got this double grid. So it's really double grid. And so we're collecting a whole lot more images, but our flight time is now 46 minutes. And so we're collecting almost double the amount of images. So when you're getting these certain drone deploys and other programs, the number of images to process, I think, if you go over 1,000, it's going to bump up the price that you have to pay if you want to do it all in one go. So that can be another challenge to think about. Is like, how many images are we processing? We want to try to minimize those. We try to minimize, but also optimize. We don't want too many images. That's going to take processing a whole lot longer, but unless it gives us an additional resolution, which we really need. So what this look like is, this is a standard a flight path. This is manually controlled flight path. Each one of those triangles at the top there, they're where we took a picture over the ground below and created that ortho mosaic. So that combined all those single images combined into one large image. And so from one of those, we can see that we're flying at 400 foot above ground level, 394 feet above ground level. We took this back in December of 21. But we can get fairly detailed. We can see about with the Phantom 4, when we're flying at 400 feet above ground level, we can see about 5 acres looking straight down. So, and that's a 2D representation. But I want to see, from this, from that created images, because we have a location, the GPS location of the drone, we can get elevation models. So we can get elevation. We can also modify. This was within drone deploy. We can modify if we want to look at, this was potential for some issues with water during this farm visit. But there's issues with some water, and definitely could tell, okay, so you're going to have this area here that could be a challenge. Do we need to think about drainage tile or surface drainage? What do we need to plan for this location here to prevent future issues? And we can also get our 3D applications as well if we want to get some 3D modeling taking place. And then also the drone deploy gives you the option for, this is just a regular camera, some plant health aspects, which we can utilize in other aspects, and I'll go into that in further detail when we jump into it. So just a real quick introduction for our sensors. So we could have a couple different sensors, really just going along that electromagnetic spectrum there. So visual, multispectral, hyperspectral, where along this are we looking at? But in the infrared region, it allows us to see and visualize some of those green, dry. We can get distinguish between some of the issues with crop stress in that infrared region. And so this is just a further breakdown, all of our RGB, so red, green, blue imaging, so our regular camera, we're just taking, and there's some overlap between the red, green, and blue, but, we're just taking those 3 bands in essence, three distinct images and then combine them together into one single image. And so we're utilizing that, for some of our simple analysis. And then there could be multispectral where we include some of that infrared, near infrared aspects. And then hyperspectral images is where we really take a really detailed approach at looking at, all the individual bands within that visible spectrum, near infrared spectrum as well. And so from a sensor standpoint, a regular camera, digital camera, in essence, is going to have the visual bands of visible red, green, and blue. We can get our orthomosaic images. We can get photogrammetry, try to pick the 3D aspects, digital elevation models, digital training models of crop height, and inferred crop height and quality. And so it's going to be probably one of our lowest cost options. The multispectral cameras are going to be a little more expensive. So they have band passes. We'll have usually very specific bands they're looking at. So 475 for our blue, green, red, and then near infrared or near infrared bands. And hyperspectral, we're going to have a lot more. But in those cases, we're also looking at specifically vegetative indices, disease and weeds, and then potentially for the hyperspectral indices, plant stress, composition, and quality. So then thinking about LiDAR is another option as well. Thermal will be another option. So we kind of have our 5 different options: red, green, blue, multispectral, hyperspectral, LiDAR, and thermal. And then LiDAR is going to be moderately expensive depending on the quality and level that we get. So really with these, a regular camera, allows us some information, but the more and more detailed we get, so the multispectral, we're able to pull off some more information and really to look at our vegetative indices. So I want to mention here LiDAR. So we have sonar, sound waves, radar, radio waves. LiDAR is light detection and ranging. So it's using that light to assess our crop as it goes from our sensor to the ground, to alfalfa, then back, to help us get that estimation of our crop height, potentially our ground level as well. And so this here shows one of the LiDAR images we've taken from Veldine LiDAR. So we've taken 16 different channels, each channel taking 20,000 points a second. And so we're taking about 220,000 points a second with this LiDAR. And so it can be a high level of data, but it can give you a very detailed analysis because it can penetrate sometimes those crops and get you a good estimation of that crop height. So how are we using LiDAR and how are we using our photogrammetry? In either case, we're trying to create a point surface or a surface map. And so with the LiDAR, it's able to scan across and create points across the top. So if it's very dense stand, a lot of those points should be high, or if it's a thin stand, we expect it to be somewhat lower. And then for the same photogrammetry, where we're getting, looking at that crop height and getting more gaps between it if we have a thinner stand. So this shows to some degree what I was talking about when we have the higher propensity for our points being higher with the thick alfalfa and much lower at the lower point with our thin stands. And similar to photogrammetry, we're creating that 3D image out of all those 2D images. So we take a bunch of 2D images around our surface and create that 3D image. So for our sensor, so getting into the meat of it, what we've actually done here at the University of Kentucky was we had 25-acre field thereabouts. When we measured, we had 21 square meter quadrats. So there's our quadrats here. We did weekly measurements across the entire season within the alfalfa field. And so we flew a Phantom 4 Pro, so 10 meters above the ground, and a 10-meter radius around this quadrat. And we're recording, we had a 20 megapixel camera, and 4K Ultra HD. And for the post processing, we used Pix 4D for our post processing. And so this is what it looked like when we had some of our quadrats out in the field and with our drone there. So it's not quite scanning, so it's moving between our quadrats there. But this would be the view. This would be the view you would see from the drone. And so this is showing what we took place in Pix 4D, or what we get from those stitched images. So we recorded video around the quadrats, and then we recorded every 30th frame, and then stitched those together to kind of get an estimation of what's available within that quadrat. So a lot of times, with drones, we can collect a lot of images, we can collect it, but the ground validation is going to be an important aspect. So with this, within that one quadrat, we were recording the average mean, what's our mean crop height, we recorded, what's our maturity within that quadrat, we recorded a lot of different parameters so that we quantify, what's taking place within that. And so we did some filtering. So you saw in the image where it had some of the the alfalfa image on the quadrat itself. And so we were able to move that with some filtering, and then finally get on the right is shown here, our surface for within that quadrat, the surface of the alfalfa within that quadrat. And so from that, we used some machine learning to get our estimation. So we used the variables for mean crop height, standard deviation, that crop height, what was our maturity. So our maturity aspects, going from early vegetative to mature. And so we did this, like I said, across the entire season. We looked at our weed pressure, we looked at our disease pressure, and weed and disease pressure and insect pressure were generally below 5% on most of these crops from that year that we harvested. And so the interesting aspect of it, so looking at a correlation to NDF, ADF, crude protein, and yield. So we were building upon some of the prior literature, which demonstrated that there's a correlation between these quality variables and the height of the crop. So as it gets taller and taller, we're seeing those qualitative values decrease. And so using that, crop height as a year, so for two variables, it just includes our mean height and our standard deviation and our UAV estimated height. We're able to see about a 0.6 R squared correlation between our mean height, standard deviation, and our new qualitative values. As we increase those, so we increase the 3 variable includes our maturity, and 6 variables includes everything, pest, weed, disease pressure. We're able to increase that resolution as well within that, what we're able to estimate as far as yield within that quadrat. And so from a yield standpoint, we're at 0.69, 0.7 as far as our estimation for our yield aspect. So with that, we're able to get relatively decent estimation of what's available within that quadrat within the field. Taking it further, so for our 2019 flight parameters, so another study we had, we flew at 30 meters above ground level, so 30 looking straight down, 30, 90 looking straight down, and then we also increased that to 50 and trying to see how does our differences in altitude going to change things. So we flew at 50, 50, 90, and then we also flew at 50, 75, where we changed that camera angle as well to more oblique angle and see does that help or improve our analysis. And so in this case, we increased the altitude and we also changed our camera angle, looking between the two. And so our resolution per pixel, so our ground sampling distance, so for each pixel that we collect, for our 3090, we're at 0.8 centimeters per pixel. So from one end of one pixel to another is 0.8 centimeters, and we go up to 2.2 for our 5075 for our oblique angle. And so here we did this over 2 different fields. So we looked at our low lignin alfalfa, then we also looked at that was glycophosphate resistance, and then we looked at one that was just glycophosphate resistance as well. And so for our 2 different crops, and we can see where on the image on the top right, where our path, vehicle path for our sprayer ran through this year. And so we're able to see that vehicle path within that field as well. But we can see the 3D image, 3D image that was collected within that field, but we still used our quadrat so we could have a definite location within that field where we measured that volume of material and the amount of material within that quadrat. So we also had our quadrats out there where we did fly a total path as well. So we did our quadrant only flights, then we had our flight 30 feet, look at 90 degrees, looking straight down. Another flight with a 50 meters, 50 meters above ground level, or no, that's 50 feet above ground level. Look, no, that's a meters, excuse me. That's got to be feet, 50 feet above ground level. And then, and then 50 feet above ground level, looking at oblique angle. And so what's the interesting thing was for these, we saw our two variable model. R squared was again 0.6 for our quadrats only, and then we saw it increase to 0.71. And we increased our altitude, so we're going from 30. So 30 had our highest R squared value, which would make sense. We get a more detailed ground sampling distance, so a much more high higher resolution, it was able to improve our quality. We increased to 50, 90, it decreased, so which is what we expected. And I think similar studies with corn and other aspects have shown, we're going to see reduced resolution, we're going to see reduced correlation between those values. However, we had the 5075 that actually outperformed it. So the oblique angle with the quadrants in the field, it seemed to perform better than our original model looking straight down at 30 feet above ground level. So that was an interesting aspect that was within this study. So but then the combined, so we took all those images that we collected and put them into one single file. See, does that really improve our overall aspect? And it did not. But we were fairly satisfied if we take our 2-variable model or even the 3-variable model, where we had our height, mean height was estimated, and our standard deviation was estimated. It was able to get a good prediction for our 2-variable model. Then we included in our 3-variable model the maturity. So maturity wouldn't be too bad if we had a producer. You had to go out there, estimate your maturity, and then we get a much better correlation as far as our quality, our yield in this case, and associated from our similar to last study, our quality as well. So we also did some work with LiDAR. So we did some work with LiDAR, collecting some 3D scans as well. And so for this case, we had our 2019 study. We saw that we were at 2 meters above ground level. We had this fixed to our quadrats, and we did 3 to 4 revolutions, about 70 points per quadrat. And we're able to estimate, the 95th percentile for our height was actually able to provide our best estimation of our crop yield, at least from a LiDAR standpoint. From our data, we tried pulling more and more insect height, maturity, other aspects, but our 95th percentile was able to probably provide us our best estimation of that for the yield. Further LiDAR testing. So this is one rig we had where we had to pretty much some work done by one of our grad students, and what I'm showing is from his thesis was that we had our quadrats, we had our LiDAR, so it's a validating LiDAR that pulls 320,000 points a second. We had it going across that at different speeds. So the reason we had that was so that we were maintaining that there was going to be no variation in our height. We can only vary our speed. And so we control certain aspects and see how much does this degrade as we increase our speed. And so our height, maximum height point was actually decreased as we increased our speed up to 5 miles per hour. So our maximum height was definitely decreasing. We got up to 3 miles an hour. It was starting to taper off a little bit, and then we definitely saw a decrease by the time we hit almost 5 miles per hour going across our track there. So we saw that the speed of LiDAR, so as we increase our speed, it's going to reduce the number of points that are within that square. But, is it also reducing our quality? And we're looking at a couple different volume measurements. But again, we determined that, probably our best estimation is just our height estimation. 95th percentile is probably a better way to characterize some of these aspects. And so what we found was, our LiDAR and photogrammetry, they demonstrated somewhat comparable. So for the same quadrant, demonstrate somewhat comparable point clouds. But we found that the photogrammetry, at least for us, it seemed to, within the quadrat, it seemed to be a better, lower cost option for us to conduct our yield and quality estimations. We also have been doing some work with some brome sage. And so I know you guys are dairy producers. You're going to have a higher quality forage. I just want to go ahead and mention this because we've done a couple of different flights with these. And so it is a native warm season grass here in Kentucky, indicator of low palatability and digestibility. Usually it's a soil fertility indicator. So it's, if we have a problem with our pK or even our pH, this is going to be an indicator for these. And there's not, a really good control for it other than soil sampling and fertilizing. But one of the challenges for a lot of our producers, and I think it's a challenge pretty much across the board, was this past year past couple of years has been the cost of fertilizer. When it really shut up there, a lot of producers, switched to some of our producers switched to a low cost, a low input management system for their hay fields and pastures, hoping that the price would eventually come down, and it's a little more manageable, I think, at this point. But a lot of them hadn't been doing as much as they should be or recommended. And so working with the producer, he had the same hayfield over a 10-year period. he fertilized annually with 200 pounds, triple 19. Looking at our soil test for his field, we were 6.2 for our pH, so fairly low pH. Our P was 72, and our K was 57. And so we're in the very low for our K. And so we talk with the producer, no, we're removing what we remove for every 3.5 tons. We're moving 130 pounds in, 42 pounds, and we're moving a lot more K. Just want to emphasize, we're moving a lot more potassium. And so the triple 19, we're just needing to show that it wasn't doing the job for him. And so he allowed us to do a couple different fertilizer treatments on his field. And so, this shows a breakdown where we had our N, P, and K at different levels. So I think our N, we're applying it either three applications, 60 pounds a piece. Our potassium, we were applying at 2 applications, either once in the fall or both once in the spring and fall. And going through this, we can see that there's definitely differences within this field, within the treatment here. But this is from 2019. But I wanted this shadow here. So over the shadow part of some of our plots, we had to drop those plots from our analysis because that shadow, we didn't think about when we were flying. So a lot of times we have to think about when we're flying for some of these. So we're within Powell County. I flew in October 2018 to 2020. This started out to be just a flight to record get some good images for extension presentations. And then it became, we actually looked at it. I think there's a difference between the plots that we can visualize. And so we went ahead and analyzed it and saw that there is. So we Phantom 4, 80% overlap front and side. We've got 0.4 inches per pixel, and it was stitched, in this case, using drone deploy. And so we looked at 2 different visual indices for this, for the red, green, blue images. So it's not multispectral. So our green leaf index and our Vary index, visual atmospheric resistant index. And so what we were able to show, at least with the Vary, was that, we saw that you can kind of see the 206, 306, and 407 and 101. They're all, aspects in which is not getting fertilizer. And so it was very easy to visualize. So anytime, we can see that. And in our stats on this, we see that there's definitely a distinction between our low fertilizer treatments and then our high fertilizer treatments. Anytime we're applying that additional nitrogen, it definitely seemed to be grouping by that. And similar with our other vegetative indices, maybe not as much resolution with this one, it would seem, but we saw that taking place. So with these, we saw that it was definitely significantly different when we had that lower, at least for the Vary, we had that easily able to see the difference. The closer we get to a value that's 0 for the Vary, and same with the GLI, we were at a much higher quality standpoint as far as our fertilizer. So we applied a lot more fertilizer. So knowing that, similar to what you all know, as we increase that fertilizer application, we're definitely able to increase our tonnage, and then we're able to work with the producer and figure out, does this make sense to fertilize from a cost standpoint? But, as far as our composition, 2019 composition, we saw that we were able to shift our percentage of brome sage just with that fertilizer application. So shift the amount of brome sage available within each one of those plots just with our fertilizer application. And so this was just with the statistical analysis. There's future work we could do with more machine learning aspects. But for that producer, we had other producers ask about it as well. Can we, estimate, how much brome sage is available? How much do I have a problem? It's like, well, if you have to ask, a lot of times we tell agents and producers, then we need to soil sample, we need to apply nutrients, at that and just look at, what, because it's costing you, because it's not going to be as nutritive for our cattle, not going to be quite as usable. So that's just with a regular camera, we're able to see that there are differences. There are, other ways we can have, hyperspectral imaging that can be done, that can provide us with some, relatively decent, that can provide us with pretty good estimations of our quality as well. So these being done by other universities across the U.S. And, just figuring out, from a research standpoint, we know what spectrum from a review that are going to be of interest to us to analyze. But anytime we have the multispectral, hyperspectral, and LiDAR, it's going to add in the cost of our drone and sensing. So I want to go ahead and emphasize this though. So our cost, I got a decision aid. So AEN 160 helps you estimate the cost of using drone in production agriculture. For our regular flights, with just a digital camera, it's $1 to $2 per acre for the flights. Is estimation. We're paying about $800 per year in minimum in post-processing software. Your drone and other equipment, initial cost could be about $2,600. And it'll vary. You can spend as much or as little as you want. Drone insurance could be about $600 per year. And if we're flying 52 flights per year at an average cost of, and doing 50 acres per flight, that's where we kind of get that $1 to $2 per acre for these flights. But it's similar costs on the multispectral and LiDAR. The LiDAR is going to be about $8,000. Multispectral could be about $8,000 to $15,000, and you might have to get a bigger drone. They can still be $1 to $2 per acre, but knowing that we're going to have to spend a little more money to get those. And hyperspectral analysis, that's currently cost prohibitive because you can get you a pickup truck or two the cost of a hyperspectral camera. And so our general workflow, knowing that we have the alfalfa, we have our sensor, and then we have to have some type of machine learning to help us decipher and determine, what is our yield, what is our quality, what is our quality parameter, and correlate that to the parameters that we measured, our height or our quality, and then going and making a decision and action. So I guess, mentioning new technologies. So the National Farm Machinery Show is the February 14th through the 17th. It's going to be in Louisville. So I just go ahead and mention that. We'll be in booth 3444 through 3,444. And we should have, at that point, hopefully our new weather app available for download. So with that, I'd like to open up to any questions.
All right. Thank you, Josh. If anybody has any questions, you can either type those into the chat or use that raise your hand function, unmute if it's a little bit longer question, easier to ask verbally. Definitely a lot of information there and some neat things you guys are doing with drones and the ability to sense that.
I got the question. What is the typical data processing time per acre? It really depends on the total number of images, but I'd say at least it could be about 1 to 2 hours for data processing time. There are some aspects where they're working on from research standpoint, can we get field edge estimation? But typical data processing, I'd say about 1 to 2 hours. And a lot of it, we're using Pix4D, which kind of tied up in one of our computers from a data transport standpoint. We just, at this point, upload it to online services like Drone Deploy. I think Pix4D also has one that's online now that you can just upload the images. So however long it takes to upload those images and still process in 1 to 2 hours, then get the results. So you fly one day, send it that night, you send it out, and then upload it, and the next morning you get your results. So usually about 1 to 2 hours for most fields, I'd say. Processing time. And something I didn't mention was ground control points. So a lot of those we're using the quadrats themselves, so they're kind of our ground control points. So that was our ground control. So either you're going to spend a little extra money on maybe some RTK on the drone itself, or you're going to get some ground control points, have at least 4 or 5 scattered throughout the field, 4 at minimum, and help you resolve some of those images. So if you're getting a good elevation, because we got alfalfa itself, it can be about 20 inches tall, and so we want to make sure we get a really good estimation of that surface from a height standpoint. So that's a good question. What and I guess and how we're using it is for. So I guess it depends. So there are people who are doing it as a sprayer or as a drone service provider. So there's a couple people within the state here that actually will go and image your field for you, and they'll charge again that $1 or $2 per acre. And so the question is, can you make whatever economic decision you're trying to make is going to be worth that $1 or $2 investment per acre? So that would be the question, I think, is and for some, if you're trying to decide whether you should replant or not, that is the one thing I wish we could get is a good, stand count essentially. But we can look and estimate that yield and try to see, are we tapering off in certain areas for yield? Does this area potentially need to be replaced? So I guess it really depends on the question we're trying to answer here. And I hate this because a lot of times, extension, but it really, we always kind of say it depends on what you're trying to do, what decision you're trying to rationalize. Because how do we pay off? What's the return on investment of that $1 to $2 per acre cost? And so a lot of it, if you do have we already have a drone itself, you're your own producer, you have to pay the annual subscription for that, post-processing software. Is that going to be worth it for you to make a decision making? And I know here in Kentucky, it's a little different because of the tobacco money and tobacco settlement. We actually get some cost share on purchasing a drone and potentially even the software aspects. So we can actually get, instead of it being a $2,000 drone, we can get it for $1,000. You get a cost share, you get compensated, you get $1,000 drone. So sometimes for down here, it might make a little more sense. They're trying to encourage some of our producers to utilize some new technologies to evaluate what's taking place within your field.